to give us a seminar. I've known Dr. Chao for more than a decade, more than 10 years. First, we met when I worked at NRL, and we met. He's one of the external science review panel for the ONR and Naval Research Lab. And then after that, we meet frequently at AMS Ocean Science Meeting. Dr. Yi Chao got his PhD from Princeton University, Atmosphere and Ocean Science Program. And then he worked as a scientist on various satellite missions. Most famously is the Aquarius satellite salinity program at JPL and Caltech for more than 20 years. Then 5 years ago, he decided that's not interesting or challenging enough. So he started his own company called SOLO-TREC, using NASA-developed technology to do thermal energy harvesting for glider and other instrumentation. He is also a chief scientist at the remote sensing system on remote sensing satellite system. He recently got awarded with one SBIR program working with NOAA and GLERO on data assimilation. So Yi is one of the few scientists that I know is expert in all three fields: ocean model development, data assimilation, and satellite remote sensing. So it's all yours. Welcome.
Thank you very much for the kind introduction. I got my PhD from Princeton University, work with GFDL, I guess one of the sister lab of the Great Lake Lab. So I'm a little bit familiar about OIR 20, 30 years ago. So I've been working at Jet Propulsion Lab for 20 years. I've been doing about three things, and then satellite remote sensing, particularly the salinity satellite, I will not talk about. This is a Great Lake Lab where we work on the Great Lakes. If you are interested in salinity remote sensing, be happy to talk to you offline, either today or tomorrow. There are two topics I will try to cover as much as I can about the instrument we have been developing the last 10 years, and also the second modeling data simulation technology, kind of my since my PhD days, and then continue to evolve and improve. I left the NASA laboratory is not quite because the work is not that challenging. It's just because I get frustrated about the technology I developed, and then I keep calling the industry and try to ask them to transition to commercial application or services and products, and it's hardly get done. So this is probably not new to many of you. So finally, 5 years ago, I decided maybe I will try to cross the fence, and I'm going to get that done myself. So if nobody on the other side of the fence. So that's kind of my motivation to leave the government to commercialize these two particular technology I've been developing as a government-funded R&D, but have a huge potential in the commercial application, but are very risky for any industry to take over because it's very early, studied in the stage of the research papers and patent in the abstract form. So it's far away from making money. So unless company have resources put in FTEs and dollars investing in this area, it will take years to get commercialized. So probably take us, extra push to make that transition more successful. So it's my first time to Michigan. How do I do this? How do I go to the next slide? Here we go. So the first thing I did is go to the web, go to my smartphones, and check the temperature and rainfall. I bring my umbrella. It's much cooler here. It's really nice. What I'm trying to make, the point I try to make here is we take for granted the weather prediction information is available anywhere, anytime. It's on our fingertip. Whenever we go, we type the zip code, all the information come out. I checked this 2 days ago and tell me about the temperature, what to wear, and tell me about the thunderstorm. I listened to the radio this morning. I drive in, have thunderstorm somewhere. So I bring my umbrella, right? So my decision based on the information I'm making. back in the PhD days in the 80s, this information is far from known to the public. You have to buy newspaper and then to get this kind of information. So this information is really critical to daily decision making for everybody, and then take enormous infrastructure to get it done, to deliver to the customers like myself, typing the zip code, getting the weather prediction. Now I maintain a huge observing systems, ranging from satellites, aircraft, weather stations, and that's almost $1 billion operation. And then plus supercomputers in Washington, and then digest those information into computer models, three-dimensional atmospheric models, forecasting into the future, and then to project the kind of the large-scale, global, continental-scale weather prediction. And then last time I did a survey, there are about 200 companies. The famous one, you probably know, IQweather, weather.com, even IBM have a division doing weather-related services. And that's almost a $1 to $1 compared to what government put in to generate so-called value-added services. So the information you and I getting on the smartphones and the computers doesn't come from NOAA, the weather service, but they provide the backbone information, enable this private industry to provide those services. So that's kind of interesting partnership between the government-funded activities, academic researchers, and then to enable those information to make available to the public. So I call that the most successful example in the earth science to linking research, R&D, and then private services. Thinking about 20 years into the future or 10 years in the future, talk about oceanography, and then what does it take to get ocean information into the same maturity of the weather prediction. So there's no zip code in the ocean or Great Lakes, but if you give you the latitude, longitude of the lakes, I ask you, what's the temperature at 100 meters or 50 meters? Nobody can tell me. So it doesn't really exist today. So we are still very early in the R&D stage. Emma?
If I could, for 1 second, just make 1 or 2 clicks. I apologize to everyone on the webinar that the screen is not clicking. Good? Okay, thank you. Sorry.
So I keep the click the same way?
Yes.
Okay, I'm doing this arrow.
Click that little orange arrow. That'll
Oh,
go
you
away.
want me to do this? Okay.
And that'll go away. Just click it once.
Okay.
Okay, now
so
you're
I keep clicking.
I
okay,
apologize.
Great, no problem. So I guess my point try to make is operational oceanography, ocean forecasting still 10, 20 years behind, depends who you're asking. So the goal is to get this technology mature enough so we can provide the ocean forecasting information the same way as the atmospheric weather prediction. So ocean forecast is challenging because collecting data is very difficult. We don't really have the weather station network that you can set up regional weather stations. How do you set up the ocean stations with people maintained 24/7? So it's much more challenging, and particularly in the open ocean away from the coast, and you need to use all those big ships. And those technology doesn't improve over part of the last 200 years or so. We do ship expedition long time ago at the first Challenger exploration. And we do the same thing even today. We need big ships. There are 10 of these ships available to the community. Take a year to reserve to go out to the sea. Costs $50,000 a day, 20 FTEs to work on the ships. So it's extremely challenging to collect data. So ocean data is much more difficult. And as many of you appreciate, if you don't have the data, modeling is always a toy to the digital ocean without reality consistency. So in the last 10 years or so, the community has been developing autonomous systems as unmanned systems. So try to not necessarily replace the ships, but also try to increase the density of the coverage. So when the successful platform many of you familiar with, we call Argo profiling floats. These autonomous floats can go down to the ocean up to 2,000 meters. This particular scenario for the Argo program, is to profile every 10 days and to monitor the climate time scale, ask the question how the ocean responds in the climate change scenarios. So the international community has been deployed 4,000 of these floats, monitor the ocean, take a snapshot of the 3D ocean every 10 days. So we know in the changing climate how the ocean responds and then feedback into the climate. It's one of the most successful international collaboration in oceanography, modern oceanography. NOAA, of course, contribute about 50% of these floats. And then more importantly, the float technology developed in the national lab in the academic institutions, and then eventually being transferred to commercial applications. So that's why this program can sustain not only in the US and also spread out in the international community. So 50% of the float provided by international community. There's a table, you can look it up and say Brazil contributes 3 floats. Japan have 50, and Germany and France and so forth, and like 30 countries contributing floats on a total of 4,000. I downloaded this picture 2 days ago. It's close to 2,000. That's a target this community is going for. There's a challenge to scale this observing system to the relevant scale to the ocean, because we are even 4,000, I put a dot as big as a little lake. And so it's really challenging to scale up this technology. The main thing, the bottleneck of the technology to apply everywhere and then more frequent or higher spatial resolution, all these floats are powered by batteries and they have a limited lifetime. So there's a paper a few years ago published and tried to document how long these floats will last. And the different colors here show the time being deployed. So the x-axis show that each surfacing, so every profiles they've been collecting. So they collect every 10-day cycle. So after about 200 profiles or 200 dives, typically battery died, you can see the float deployed 100% start to drop to close to 0%. So some float lasting can make a little bit more than 200 profiles. Many floats fails even before 200. So if you took an average, is draw a line there somewhere between 150 and 200. So 200 is a good number, and because each one of these floats costs about $20,000. So 200 is easy to do the math. So you can quickly do the math to maintain these 4,000 floats. Is 4,000 in the global ocean, take about 3 degree by 3 degree, 300 kilometer separation from each float, and they profile every 10 days. You can simply do the math, and each profile costs about $100, and then it's about $20 million to maintain this operation. Now I put in 10 million of these, and it's still very doable to do a global climate monitoring with the CTD only, measure temperature and salinity. So as the community science demands increases, there's a Argo program is being kicked off recently. Try to add more sensors, nitrate, oxygen, pH, more ecological relevant sensors to the system. And you can see the float costs go multiple times. Some of the nitrate sensor costs as much as the platform itself. So very quickly, you can grow the cost of the float into 2 times, 3 times, even 4 or 5 times for fully loaded biogeochemistry floats. That's increased the cost of the profile as well. So set aside those instrument additions, just to simply increase the resolution or the temporal sampling of these floats to get to the number very quickly the community cannot sustain. If you want to do 1 degree by 100 kilometers rather than 300, that's go almost $1 billion to maintain an ocean observing system like this. And if you say I want to resolve the day and night and sunset and sunrise, and then you're going to do 4 to 6 profiles per day, and that's give you the cost increase even to multiple billions of dollars. Forget about today's environment. Even in the ideal scenario, there's no way this kind of observing system can be sustained to enable ocean prediction like the weather prediction. So have to be something, a dramatic difference technology come up. In addition to the funding constraints, there's also a logistic challenges because when we put in a few hundred, a few thousand of these floats in the water, we don't really care about what we leave behind, because all of these floats are disposable. Many of you may not be realized this $20,000 is very small compared to the ship time. Ship time cost, if recover a float, costs more than the floats, right? So become a disposable device. And then what I put in here is all the historical float being deployed in the last decades. So the red dots mean all the float, the last reporting position. So basically they get buried near that red location. So basically I call it dead floats. And each float carried 10, 20 kilos of lithium batteries or acid-based and chemical batteries. And then so the impact on the marine system, as we put in more and more of this observing system, thousands of, tens of thousands of these, and it become really challenging to imagine the environmental consideration and then ecosystem. Forget about at some point at the time you have to pay taxes to manage the waste batteries, just like we did in our land. So that's another constraint of this technology. So thinking about cost reduction, more data in the ocean, and then reduce the pollution of the toxic batteries. And that's really drive the new thinking about how to develop a technology you can sustain, you can scale up. When I started this problem as a remote sensing satellite oceanographer, is try to do a calibration and validation and look into this problem about 10 years ago, and then start to do a survey of this technology and just realize this is one of the areas certainly need a lot of R&D and need a lot of attention. And I was really surprised it's not being looked at it. And we are busy buying new gadget rather than thinking about what these gadgets limitations are in very early on in the game. Another point I want to make for those students in the audience is a lot of these ideas is being thought about. I'm not the first one to propose these concepts and how to scale up this network into a finer resolution, more frequent sampling, as I mentioned, at the reasonable cost the community can afford. If you throw all the money, if a DOD to put this float, no problem. But if we put environmental monitoring, there's no way we can bring the billions of dollars to this observing system. And I have to be environmentally responsible at some point. If there's no tax today, there doesn't mean there won't be tax tomorrow. So one of the lessons for the students and the younger junior scientists, and then we tend to stay away from the library because everything electronic, right? So it turned out this concept was proposed is by our famous Henry Stommel, as many other concepts, and he published even a paper, 4-page article in the Oceanography magazine back in 1989. Looking back, this paper probably cannot be accepted today because there's no results. It's all dream and ideas. In the back old days, and probably you can publish a dream paper and the 4 pages, just a science fiction. In the peer-reviewed community, you'll probably get 2 bad reviews, and then you won't get published today. But Stommel at that time dreamed about this float even before the first Argo float appears. He talked about this float and have to be powered by thermal energy in the ocean. There's a vertical temperature difference in the ocean. There may not be too much stratification in the lake, but there's 3/4 of the global ocean have a significant temperature differences. Is unlimited thermal energy deposited by our sun. And he even talked about the ocean observing system have to be multiple times per day, just like a set release weather balloons on the weather station. And he estimated at that time roughly take 1,000 of these floats to do ocean observing systems. Order magnitudes is correct, right? 4,000 Argo floats. And then if you read the paper, he even talked about all this data available real time. So back in 1989, in his cottage, and he were able to see every data sets reported back from the thousands of floats, and he can synthesize them on the wall. And this is before Google Earth even exists. And then he can use that information to predict the ocean, just like weather prediction. It's an amazing article. If for the junior scientists, we'll be encouraging you to go to more libraries and then read these kind of articles. So I was intrigued by this article, and I was able to go back and turn and surprisingly, pleasantly surprised, and then nobody have followed through. And there's the patent applied back in there's a patent being submitted back in even '89, and by the time I got started, they are 3 years from expiration. So it's pretty intriguing to think about this technology being proposed decades ago, and then to sit there to be realized. I mentioned ocean thermal energy, and as you know, the thermocline, the stratification occurs to 3/4 of the global ocean, and that's really a free energy we are not tapping into to help us to do this ocean observing systems. So I started this about 10 years ago, and then, as you know, getting to go to the director, getting a small amount of seed money, writing a proposal to NASA to help get it started, and eventually ONR funded us to do a prototype development. This is back in Caltech and JPL days, putting an engineering team together. I'm an oceanographer. I'm not an engineer, so I put in the requirements to the engineers and engineers to develop this concept. There's 2 patents being proposed that time, and now is granted already. So the idea is quite simple, is to thinking about how to convert this relatively small temperature difference into electricity. So converting temperature difference to electricity is not new. Steam engine, you can burn coal and then boil water. Water expand when they evaporate, and then when they evaporate, they're changing their volume. They push the turbine, drive the train, and then turn the electricity. The generator generate electricity. So the temperature we talk about much smaller. But there are plenty of materials, unlike water, to change phase, not necessarily from liquid to gas, but from solid to liquid. So 10 degree C difference is the one we are working with. And we identified a number of different chemicals. They changing phase from solid to liquid, and then within 5-10 degree range. And they give you a significant volume expansion, not as big as vapor and water, but you can see in the lower panel, you see that 10%, on the order of 10% expansion every time you cross the thermocline. So it's a small amount of expansion, but the point is it's free, right? So if you accumulate, add them up, and you can harvest pretty significant amount of energy. Is completely scalable. So more material you use, more expansion you get, the more electricity you generate. So the schematic on the both sides is show you, if you put in this material into those containers in blue, and then when you get to the surface, it's hot, it's gonna go through this transition from solid to liquid, and then expand 10%. And then the orange color is this hydraulic liquid in the middle. When you expand the material, and then you put in the solid container, they have nowhere to go except to push this flexible tube inside with oil and then squeeze them out to create this pressure to rotate the motor to generate electricity. You can charge your battery. So imagine every time you go through the warm and cold, cross the thermocline, you can do a energy production every time. So that's kind of the fundamental principle describing our patent applied at that time. So we put into practice. This is funded by ONR. To develop these first prototypes. We essentially putting all those phase change materials in the side, is essentially putting in the floats, and then have design almost a backpack on the floats. You just put in the phase change material tube on the side, and then eventually they cross the thermocline, they generate electricity, and you consume energy as every time you dive, but we also generate energy. So you can see many of these tubes, so we kind of generate sufficient energy to provide 100% of the energy to power the buoyancy to go to up and down, and also to power sensor like conductivity, CTDs, measure temperature, salinity, the communication and the surface, talk to the iridium, and also the computer control the entire system. So it's essentially a self-powered float. So once you're deployed, you never have to worry about energy consumption, because it's a free power. You can profile as frequent as you want, and without punishment of reduce your lifetime. Like Argo float, you can profile 4 times a day, but your float will die very soon rather than a couple of years, right? So we did this test near Hawaii back in 2009. This is before I left the government. So we recovered the float about 2011 or so, and then this float survived 18 months, completely powered by ocean thermal energy, making every one of these dots here represent an 8-hour sampling. So we do a three time profiles per day and over 18 months period, and we were considered as the first self-powered underwater robots. There's about 6 self-powered robots on Earth, and there's a Popular Mechanics magazine survey of the 6 different robots. One of the funny robots on land is the biofuel harvesting. Basically, you harvest the corn, you generate biofuel, you drive the truck, harvest more corn. So once you have a corn, your truck will run forever. So that's kind of self-powered trucks, but you have to run in the cornfield. Once you get out of the cornfield, the truck will die. So in our case, it's really self-powered by temperature difference. So as long ocean thermocline have a 10 degrees C difference, we can continue to profile. Of course, once you go to polar areas, then you run your batteries. So same thing, run out of corn. So this is kind of the data we are getting. The science, this is very typical. This is temperature, salinity. Really what I'm trying to point out here is that we convert into a very large pressure difference, about 3,000 psis. For those people familiar with engineering, 3,000 psi, you can shoot your gun far away. And then when we turn the motor, we generate about 300 watts during that period. So every time we cross the thermocline, we can harvest that pressure difference, and we can generate 300 watts once we turn it, the generator. So that's a sufficient power to power our device. This is kind of the first part of the mission. First 9 months, we do a daily sampling. This is the temperature, salinity, temperature on the top, salinity on the bottom, in the upper 100 meters. The first period, we sample 3 times a day. The last period, we sample every 10 days, just like today's Argo floats. So you can tell by sampling frequently, you're capturing not only the diurnal cycle, the tides, and also the day-to-day variability, sub-seasonal, sub-monthly variability, which is you cannot get from a typical 10-day sampling. So moving forward in time, and Phillips this morning make interesting comments. They said we certainly survived the 5 years as a new startup company. 90% of the company die within 3 years in the U.S. statistics. So we certainly survived the first 3 years. Took us 2 years to license the technology to my own company. It's my own invention, but doesn't belong to me, belong to Caltech. I'm sure university have the same problem. Once you license, and then in the last 3 years, we developed a commercial products of these floats. The float I designed in the prototype, as you can tell, is big, is expensive, is bulky, is difficult to work with. And that's the R&D prototype. And then when you get to the commercialization, that's the challenging, is less R&D, is more engineering, because we need to make it smaller, lighter, and then more importantly, have to be cheaper, because it took us $2 million to make the first prototype. And our guidance to the engineers, we have to make this battery, which is shown in the middle, have to be under $20,000. So that's 2 order magnitudes cost reduction from parts and labors, and then have to be involved, because we cannot sell this battery more than the floats. So I'm happy to announce that our product, we're collaborating with Seabird, making their floats. This is the standard Seabird float on the left. We are ready to deliver to Seabird about the 4th quarter this year. And then so you can buy a Seabird float with either lithium battery from Seabird or our thermal recharging battery from SOLO-TREC. So basically, depends on how many sensors you carry, what's the energy consumption you carry, 1 battery, 2 battery, just like you power your own device at home. So basically, we are fully redundant systems. So each pack of this battery generate about 7,000 joules. So if you're familiar with engineering units, that's about 1 point something watt hours, and that's about 60-70% of the Argo floats. If you have a fully not loaded bio-Argo float, you need 2 of these. So on the right picture, where you need to buy 2 of these for a fully loaded bio-Argo float. So that's looking forward to the commercial sales, and then many of our investors, including our sponsors, really looking forward to the company have real sales, and then so we can sustain and scale up. And that's really a major milestone all of my team working towards in the last many years. So that's the kind of the first part of my presentation about how to collect more data in the ocean. I'm very optimistic. 10 years later, we should have the technology. We can collect as many data as we want with the same amount of money we have today. So rather than 2 times order of magnitude to collect more data. So once we have the more data, how do you turn the data into an ocean forecasting system like the weather prediction? If we have the ocean, unlimited ocean data, how do we work with the satellite surface information we have and then put into computer toys, and then to make sure we are generating information our customers or users are looking for, either navigation, emergency response like oil spill response, search rescue, or the ecological forecasting, you name it. User define the needs, and hopefully we can deliver those products. So each one of these arrows here represent a major activities need to be done. You need people collect the data, you need the people design a better model, and then you need users to help us design the product so we can deliver to them. And then the red circle here I want to talk about is one of the key components of the technology is how do you merge the data with the model. We call it data simulation. And there's data simulation can also use to design observing systems, which is I'm not talking about today, but that's also a very important piece of the puzzle. And how many data are sufficient for the particular problem you want to forecast. That's also a very interesting scientific question as well. So data simulation is one I'm going to cover. So most of this work funded, again, started from ONR, NASA, and then eventually NOAA. NOAA support many of these ongoing data simulation operations, integrated ocean observing systems. I work with 2 of these regional associations. There's a Great Lake Association here. So California is big enough. I have more than 30 million people. We deserve 2 RAs compared to 1 for Great Lakes. So I'm working with both Northern California and the Southern California RAs, and then to come up with the end-to-end ocean forecasting system. So we have been developing this system over a long time. We have about 30 papers so far since 2002 is my first proposal funded in this area. There's data simulation papers and series of papers listed on the left, and a number of the model validation, model implementation papers on the right. I'm happy to give you the list. If you're interested, send me an email later. More importantly, as we develop better models and then develop sophisticated data simulation systems, you need to validate them. Sometimes have a better tool doesn't mean you have a better outcome. So if a mathematician, you're always pushing for the better tools, most advanced technology, but doesn't necessarily solve a practical problem. So hopefully that makes sense to many of you. Same thing for meteorology, and took many years to go through a very simple system and then to a sophisticated system. Part of these criteria to move from one system to the next is through the validation process, evaluation, systematic evaluation. I'm glad to hear from Phillips, you have a yearly campaign in the Great Lakes. Same thing for the ocean. We do field experiments a number of times to validate our system. We did 2 experiments in Monterey, very intensive campaign, 2003, 2006. This is all funded by ONR. The early days, the picture on the left show you the intensive observing system during about a month period. In the ocean environment, we cannot do the whole season. It's just everybody's too tired after 30 days, even putting together 20 gliders and ships and drifters, and after 30-day operation, daily briefing, and everybody get tired, and requires ships as well. So there's a special issue published, deep sea research on the left. We also tested in the Alaska, Prince William Sound, Before the Gulf of Mexico oil spill, and there's a Exxon Well-D oil spill is the biggest at that time. So we picked Prince William Sound for emergency response purposes, and then we did an intensive campaign 2009. That's part of the NOAA IU's activity, Alaska Ocean Observing Systems. There's a special article issue in the Continental Shelf Research. There are about a dozen papers published, and then also a summary paper in the BAM magazine to highlight our ocean forecasting systems. So I will say a few words about this data simulation in the context of a California system. This is the system we're running 24/7 kind of quasi-operational ocean prediction. We are not allowed to say we are truly operational, because if there's earthquake in LA, and my system will be down for weeks. So that we are not quite operational, we are quasi-operational. We're using ROMS model. This is one of the community open source code, ideal for coastal processes. Have a resolution of 3 kilometers, 40 vertical layers, forced by NCEP atmospheric forecast. This is older slides, and then I said we start with 12 kilometers at that time. Now we are using 3 kilometer model for the NCEP regional WRF model. We are using the global model as a boundary condition. This is the Navy HICOM 1/12 of degree, and also we're forcing tide in the boundary, so we fully resolve the tides. The data simulation we have been developing over the decades is using 3D VAR. I will say a few words in more details. Allow you to assimilate almost all the data we have been collecting from satellite, the temperatures, the height, the profile data from gliders, moorings, and floats, vertical profiles. And then in the coastal area, we also surface velocity measured by high frequency radar. So one of the key velocity measurement, very few. We have more temperature, salinity, water level, but the velocity data is very hard to get by. I think you measure velocity here with ADCP, surface drifters as well. We're doing nowcast every 6 hours, just like weather prediction centers, and then we issue a 3-day prediction every day. So we're running at the night, and then the forecast available the second day in the morning for people. When people go to the office, they have a 3-day prediction updated on their desktops. So to summarize the data simulation technique, this is a kind of schematic, kind of 3D VAR 101. It's a variational techniques. So typically you have the data collected. In this equation, you put in y as observation, and then you can think about x is the model. X is 3-dimensional in space and 1-dimensional in time, and the multiple variables is 5-dimensional array. And then you have a subset of these measured by data. So y is only a small subset of the x. And you have a metric h, you have to convert the model into the map on the data points, right? So that's kind of the second term on the cost function, the j. And the idea of this j is to do the model data difference. That's so put in the plain word, the cost function is just to take the model minus the data, see what's the difference it is, and then you square them. And then the goal is to minimize the cost function. So the goal for data simulation is as you start to assimilate more data, your model look more and more like data. So that's really what the data simulation is about, is to have model after a series of data simulations, kind of model get trained, you'll then get smarter, and then you'll behave like a real data. Of course, if the data goes away, the model will diverge and do their own thing. So if you have a continuous data stream coming in and then kind of holding hands with the model will walk along the data and then getting the phase right, get the amplitude right, and then you can do a prediction, and then people can use this for forecast. So basically you compute this minimum cost function, you derive the correction. That's the delta x. It's the increment, the model increment. So the question is, if you make a correction over all the thousands or millions of possibilities, the cost function will be smaller in the future. So that's really what the variational technique is about, is how do you do the small correction every time, and then the next prediction, you know, the misfit between data model gets smaller. So that's kind of the cost function minimization, depends which community you're coming from, and then the terminology you're using. So we have been developing a few additions that we call it unique implementations for the standard 3D VAR. The first innovation is to control the data simulation, not only the variable you're measuring, but also you derive other variable you're not measuring. So for example, you want to derive the velocity, make sure velocity is realistic by measuring temperature salinity. So you use the geostrophic constraint. So if you measure temperature salinity, you assimilate into the model, my velocity is consistent and also being improved. Sometimes you can correct the temperature for the wrong reason, your velocity gets worse, right? So in our implementation, we make sure we are correcting velocity is compatible with temperature salinity, follow the geostrophy. So that's kind of the constraint within 3D VAR. Whatever correction you put in have to follow this bottom formula, satisfy geostrophic relationship. So that's our first innovation. The second innovation is in order to measure the height is not directly assimilated into the model. We are correcting the temperature salinity so that in such a way our dynamic height is consistent with the correction. So we are not doing statistical projection like many of the other models doing, rely on statistical empirical correlations. So we are really do a dynamic adjustment of the temperature salinity so we can minimize the height difference. So that's kind of our second innovation, is to follow the hydrostatic relationship. That's the bottom equation on the left. So those are the 5 variables we are perturbing due to the corrections: the temperature, salinity, and the velocity, and the water height. And then I can go through the mathematics. We are not directly correcting the velocity u and v itself because they are vector forms. So we rotate the velocity into a stream function velocity potential, so they have much better property when you do mathematical equations, doing metric manipulation. So we work with 2 scalar rather than a vector. So that's a mathematics paper I'd be happy to share with you offline. So that's the innovation number 1. Second innovation, one of the biggest problem is how do you spread the data? We always have sparse measurement. We have one buoy, we have one drifter, we have 1 point measurements. How do you reconcile the different measurement, different point, and different uncertainty, different error statistics? So that's the second innovation we come up with. We have a mathematical way to parameterize the 3-dimensional correlation. So there's no computer on Earth can store the 3-dimensional correlation in the globe because we have millions of dimensions, and each point have to be correlated with everywhere else. So our matrix can be gigantic. There's no storage allow us to carry that correlation. So what we did is to run the model ensembles to compute the correlation. As I show you a few of these in the map here, is if you have a measurement near shore, you're going to have a smaller correlation because the scale is smaller. The spatial scale is smaller near the coast. When you move to the open ocean, the scale is much bigger. So that's one characteristic. Another characteristic is, at least in California, near the coast is more elongated along the coast. When you go to the open ocean, it's more circular. So those are the characteristics of the correlations. And this is all computed by the ensembles. And when we do the data simulation, we have a mathematical formula to parameterize this correlation. So rather than store them, which is nothing we can do waiting in time with the storage get bigger, is we're computing on the fly, we throw them away, next time do the data simulation, recompute again. It's a simple mathematical formula we parameterize easily. It's much easier to compute in many cases. And at some point, we don't store the data anymore because we're easy to recompute, so computer get faster. So that's our second innovation. Our third innovation is deal with the sparse data and the high resolution. The first generation assimilation we did earlier is we combine all the data into our system, and then turn out we get the sparse data get neglected, and we get overwhelmed with the satellite measurement by 1 kilometer SST, for example. So the high resolution always win because they have more data all the time. And then the sparse data sometimes could be very valuable. You have a glider, you have a mooring, and strategically probably better than 100 data points from the satellite pixels. And then that doesn't get a win in that case. So we eventually learned how to separate the data set at least to 2 different groups. You can separate multiple groups, but at the minimum, we separate into a low resolution and high resolution. High resolution could be coastal radar data at 1 kilometer, could be the satellite SST at 1 kilometer, GOES SST 6 kilometer, and then you have these sparse measurements. You have the buoy data, you have Argo float, you have gliders, and then you have 1 profile per day, or it's just 1 single point. And that single point data, we group them into a low resolution, so we can afford a much larger correlation scale. So we can give them more weight to influence more in the area rather than just influence nearby. So that's we can, low resolution, we have much bigger decorrelation scale. So we do a 1 data simulation the first round to generate a large scale fields, which is we call the XL. So that's a large scale to do the first round, and use that as a foundation to bring the high resolution data. You use much smaller decorrelation scale, adding eddies and filaments and coastal processes, and those high resolution data have much influence in the local area. So that's turned out is a very successful implementation. I think NRL is following similar multi-scale data simulation as well. So then a few slides of the validation. I mentioned earlier the advanced techniques not necessarily give you better results. Sometimes the better model mathematics not necessarily help you to solve a practical problems. So we have to do a validation. So in terms of the impact of the data, particularly you bring a very large amount of different type of data with different error statistics, and what's the impact of this data, and how do you decide if you do a field campaign, you're going to do more wave glider versus profiling glider, or you have more buoy versus more drifters. And everybody want to sell their gadget, right? So I want to bring 100 moorings. You have unlimited amount of money. And then how many moorings is sufficient, right? So those are the questions you have to address. And then what's the impact of this data simulation to the end product? What's the goal? If you accomplish the goal, search rescue, that could be one criteria. HAP prediction could be a different criteria. So it depends on the question you want to ask. You want to demonstrate impact of data simulation. And also you want to validate them with independent data. At some point you blend all the data together, you have nothing left to validate. So that's not good either. So we did both to validate them. I will show you the first one is more like a consistent check. Well, this is the satellite data we are simulating. The picture on the top show you the model data differences over July 2012, 1 month period. You can see near the coastal area, we have large errors. The bottom panel show you how many pixels we are simulating. That's showing the green bar. So you talk about 100,000 pixels being assimilated. It's a huge amount. There's an interesting seasonal cycle. If you visit in California to spend a few days in California, particularly Central California, you'll be cloudy in the morning, could be cloudy many days. And then you see that in the summer months, starting from June months, probably July is the worst time to go to California because most of the time it's cloudy and it's cold and cloudy. So you can see that. You can see the data significantly decrease because of cloud, because infrared cannot see through cloud. SST data drop almost half because that's a lack of data. And you can see that the blue line show you the RMS error of the model forecast. And you can see as soon as you drop the data, the error increases. It used to be we have a 0.3 degree error. Now we almost doubled because we don't have many satellite data to work with. So that's kind of encouraging to see the consistency with the data, with the quality of our forecast. This is a coastal radar. It's a radar sees through clouds and the fogs, and then you can see the data availability is pretty constant. This is to show you the daily time scales. Every day we bring about 27,000 pixels of 1 kilometer velocity in the California coast. That's a lot of pixels. And then the line there, the crayon line, show you the RMS difference. So we are about 10 centimeter per second uncertainty. If I tell the Coast Guard, they were asking me, what's uncertainty if I use your model prediction to find someone lost 2 days ago. I said about 10 centimeters per second. So they can build in that uncertainty into the search rescue operation. So there's a marginal area they have to search more. So so that's kind of the uncertain. Not only the model forecast is important, the model error is also very important. This is the glider comparison. I will not go to too much details. I will skip this. Just to saying, glider is moving platform, measure the profiles. When you assimilate the data, the red and blue show you the impact. You see the reduction, not only the surface. This is a validation for a ship program in California. So you can see the similar thing. We do this historically handcast. We also do this real time. I will say a few words about our user product. We produce temperature, salinity, and netcdf files. And then some sophisticated users is great. Give me the netcdf files, and then I will work with. So this is one of the super users we have. It's an office in Seattle working the response restoration, particularly focused oil spill response. So when there's oil spill, they can access my data every morning. Every morning, automatically, no human in the loop. The data being generated in my computer in Pasadena, and then being FTP'd to ships to an OpenDAP server to Seattle, and then the people make decisions, see this on their desktop. They don't have to call me up and during the weekend or something to give me the data. So this is one type of application. There are a couple of oil spills in the last few years, and they were able to use this West Coast model, my higher resolution than the global system now on Navy is running. Another super user is a Coast Guard. When I was a researcher at the NASA center, I underestimated if I generate the data, how difficult for the user to use them. Maybe a week or two, they can grab the data, learn how to run it, right? So it turned out it took me 3 years to put in the database Coast Guard can see. It's a tremendous amount of effort. It's not necessarily technical, but the language barriers and logistic. The pilots on the helicopter have no PhD in oceanography. They don't know netcdf files. So you have to go through a very rigorous data transfer process to get into the database to be compatible 100%. So now the Coast Guard pilot can put on the manual, see my 3-kilometer forecast. They can plan the search rescue operation. So the graph in the bottom show you the impact of HF radar data simulation. If I have the HF radar data simulation of my model, I will be able to improve the forecast by at least 30% by not having a data simulation. So that's the crayon curve with our green curve. The middle curve actually show you the historical knowledge. If you're just using the tides, you can do part of the story, but not quite as skillful as a model. This is one of the things, not necessarily Coast Guard have resources, have a contractor to package the data. I also have requests from high school teachers, from regular users, squid fishermen, and you name it. You'll get an email from someone you never imagined when you put the information on the web, and they know nothing about ocean model. They know nothing about netcdf files, and then more importantly, they have no computer of any kind to process the data. Forget about running MATLABs and so forth. So basically they said, I have a smartphone, I have a terminal, and then tell me something about your model prediction. So it's the minimum requirements. So this is a tool we developed to kind of show our layman users, and then you can go to our server, you can drop your particle, or could be a larvae, could be an object, you rubber duck, you drop in the ocean. You can track the 3-day prediction with our model. And this is fully interactive, only require a URL, and you can track this with time. So this is another product, kind of user-driven product we have been developing. Turned out it's really popular. It's a very small effort from our side, but it's extremely popular on the user side. So we are able to slowly bring the ecosystem model. I will not talk about this. I'm just saying we are coupled with the NPZ model called cosine. We are generating this model output real-time, the coupled ecosystem, to enable ecological forecasting. And our model is used by this kind of the statistical HAP prediction tool. It's already quasi-operational in Central California coast. And you can see our hydrodynamic model is combined with satellite measurements using statistical approach established to use the model fill the gap of the satellite measurements. Satellite measurements have gap in the clouds, and also they are not measuring every variable HAP prediction needs. So hydrological model, ecosystem model provide that information. So we are doing this every day. Clarissa Anderson developed this for years, is quasi-operational, ready to be transitioned to operation. NOAA is also involved as advisor for this West Coast effort as well. So just to summarize, been talk about weather prediction at the beginning. I myself certainly benefit from the weather information available on my fingertip everywhere, anytime. I hope operational oceanography will work the same way. And then if weather forecast is the most successful example, we hope to be the second most example, maybe 5-10 years down the road. One of the projects I shared is this energy harvesting technology. We are a few months away to sell our first products. So hopefully we will be playing a role to enable ocean observing systems at the same cost, but to collect more data. 3D VAR is a major tool. Hopefully have a more interaction with the lab here, and then I'm start to learn the Great Lakes and the first trips. Hopefully, and many trips to come. I landed and drive to my hotel in the dark. I open my window second day. I see, wow, Michigan. That's great. So many of my friends start to moving here. I say, how come people moving to Great Lakes? And there got to be a reason. So I hope other thing I want to convey is transfer government funding R&D to commercial product applications. I enjoyed last 3 to 5 years to do so. I hope I spent 20 years in the government labs. I hope my 10 more years to help to play a more role in this transition to commercial application. That's where I want to be more effective. I realize there's too many of us go to ocean science meetings, and relatively few PhDs interact with users. And then because we think this doesn't require a lot of math, a lot of physics, but actually it's much more difficult than I anticipated. So it's very challenging, it's very useful, it's very rewarding. So I hope to convey that message. And if you want to help the commercialization transition, it's a very notable task, it's a very important task as well. So I have my emails here, my phone number. I'll be here today, tomorrow. I hope to chat with you more for some of things I didn't talk about. And so if you have more questions, and email me or talk to me later. Thank you very much.
Any questions in the audience first? Use the mic, please. We have a remote participant.
Yeah, this will be an ocean question. When you're using the large network of Argo floats, you talked about that being something to enable projection of ocean dynamics and analogous to the radiosondes that are used in the atmosphere, and Stommel brought that out. But I guess I'm wondering what time scale you're envisioning that prediction happening over.
Are you talking about
will it be able to extend predictability to, say, the decadal time scale?
Oh, I see. Well, there's two different time scales. I think if you do decadal time scales, the Argo network probably good enough today. We have 10 years of data already. I think the challenge is to extend the modeling front, how to initialize the model to predict on the decadal time scales. That's a modeling question, I think a data assimilation question. On the shorter time scale, on the weather time scale, I think we don't have enough data in the ocean to make that prediction, and that's require increased data sets like radiosonde to launch a couple profiles per day over the area of interest, and then require many of these because ocean spatial scale is smaller than the weather. So you need many of these radiosonde in the ocean. So that's given our technology, and I hope I do, not only from a company point of view, from a scientific point of view, I do anticipate we are ready to make that jump to deploy this observing system. We enable the weather prediction. So hopefully 5 to 10 year time range, you will see You would type in the latitude, longitude, you put in any depths, and then someone in the app will give you the temperature, salinity, the nitrate, the chlorophylls, and doesn't exist today, but I would be disappointed if we don't see that in 10 years. Did that answer your question?
Yeah, the data simulation, you have a high resolution data, you have low resolution data, for example, one set, one transect or one, I think, CTD modeling, for example. How do high resolution, I think the model is easy to converge to the data. And how about the low resolution? How do you, what kind of technique do you use to let the model converge to the data? That means the J minimization of cost function J can be achieved.
Minimization is the same. It's really the only difference is a decorrelation scale. So by using low resolution, we use much larger decorrelation scale. So for example, in the California Ocean, if you have smaller correlation scale, if you have 10 data, you have 10 data point, you cannot cover the whole domain. So in the next increment, the model quickly forget about the data. But if I increase the resolution, I only need a much smaller number of data to cover the entire domain. Now the entire domain feel the state of the ocean. So that's more effective to correct the mean state, more like a bias correction. Is the most effective for the low resolution is correct the bias. Slow motion by using larger decorrelation scale.
So you can basically use the mean state of the
yeah. The second high resolution data simulation start with the mean state already from the low res assimilation. So you already have a better mean state. All you need is just bring eddies and small scale processes to it.
So I have a question over here. So I'm curious about assimilating drifter data. So even thinking trajectories, even the best designed drifters aren't exactly measuring the current that your model is simulating, right? So they could be contaminated by windage or Stokes drift or something. So if you assimilate to data from that observation is not exactly in line with what a model predicts. How do you approach that?
Well, the data we work with is primarily the more ocean current by 1 meter or 10 meter drifters. So it's different type of drifter like the ball. You have 1% of the wind or 10% of the wind, depends on the surface area. So the ocean drifter is more below the surface. So wind effect is minimum. The other question is, even though you have a surface drifter, there's still a way to do ensemble approach to approximate the windage. In our case, we diagnosed our potential trajectories. Sometimes drifting body, we don't know, is 1 meter, is 10 meter. Could be, for example, in the most recent experience, we have a dead whale in the ocean near, we know it's 100 miles from the coast. It's just drifting on the beach. The Coast Guard drag into the beach, to the ocean, and then show up next week again. It's a dead whale. It's a huge whale. So how do you know it's a wind, the surface current, or a 10-meter current? The whale go down tens of meters. So basically, we do ensembles, and then we kind of predict ensemble trajectory like hurricanes, and then we can tell the Coast Guards, and there's a likelihood, giving all this scenario, we don't know what the factor is, but at least we can say this is a corridor you want to avoid. You'll find a different location, and then they will go to the open ocean. So there's maybe a statistical way of distinguish the data with different wind contribution.
I have a question regarding the arrow, background arrow covariance. I think you mentioned you kind of predict that through an ensemble perturbation. So you don't use a stationary B, you update.
Well, we have a stationary B, we update it monthly.
Oh,
so it's a seasonal cycle. We don't update every cycle.
Yeah,
because that's where be very less reliable as time is more time consuming.
Sure. And so that was basically calculated based on your ensemble generation relative its mean to.
Yeah. Yeah, we generate thousands of those runs.
How many? Yeah, that's my next question. Thousands?
We generate decades long.
Okay.
And then so you can use that truncate into many realizations. You have, I don't remember the actual number. So we generate more than 10 years of runs, and then multiple wind perturbation, and then you can perturb with different winds, and then you can run multiple decades, and then you can truncate a certain part of the run, and then you form multi ensembles that way.
Okay.
So at least hundreds, if not, I don't know, 1,000, but many hundreds.
Okay. So the model you used to generate the ensemble are the same.
Yeah.
But the forcing are being perturbed.
You can perturb the wind. You can use NCEP wind. You can use NOAA Navy wind. You can perturb. We even do a SVD wind perturbation based on 1 meter per second and that kind of thing.
A question I have, particularly based on my past experience, is it's using a multiple ensemble to do the perturbation and estimate error covariance. There is a big challenge to me is if this model has a systematic bias to the true state, then whatever the error covariance are estimated does not actually represent the error between the model and the true state.
That's a good point. We do have bias in the model. The model is drifting, and that's why we designed this multi-scale data simulation, because we use the low resolution is essentially serve as a bias correction because to prevent the drift of the model. We have enough gliders and floats and the moorings to use a low resolution to correct the mean state. So that's a really a good way to control the drift, because initially the model we run after 3 years, the model kind of salinity go crazy, right? So drifting to an unrealistic range because there's no way to correct the mean state. So then we kind of designed this multi-scale kind of precisely address this question. We could improve our B. And another thing I want to emphasize, we also perturb the boundary condition. We have a high con, we can perturb them as well, not necessarily on the surface. So it's not a perfect solution, but we kind of mitigate that problem by using low-res data simulation.
Just my last question: what is your base to define the decretion scale for the low resolution data set and high resolution data set?
Well, that's a little bit arbitrary. If we could have 3 different scales, and then we typically high resolution on the coast, California coast, we typically on the 20-30 kilometers, the large scale about 50-60 kilometers.
Okay.
Thank you. Thank you.
Quite open tomorrow, so just let me know and I'll schedule a half hour.
Muted.